Welcome to the deep dive. Get ready. Because today we're pulling back the curtain on something really fundamental.
Yeah, absolutely fundamental to how your computer works.
And crucially, how it impacts the speed of the data structures you might use, whether you're coding or maybe just curious about what's really going on under the hood.
We're going to unpack the core concepts of computer memory and cache. And our guide for this is the Memory and Cache chapter from Hello Algo.
Which does a great job, by the way.
It really does. Breaks down these foundational ideas very clearly.
So our mission today is to help you really understand how storage operates inside your machine. You know, from the biggest, slowest parts to the tiny, lightning-fast ones.
And get to the why behind those performance differences.
Exactly. Especially when we look at basics like arrays versus linked lists. We want you to walk away with a lasting insight into why some things are just faster than others.
And the core idea from the source is pretty powerful.
Ah.
The actual physical structure of computer storage, it's not arbitrary. No, it directly dictates memory and cache efficiency. And that, in turn, has a huge impact on how well algorithms and data structures perform.
So understanding the physical side is key.
It really is. If you want to build efficient systems, you need to grasp this.
Okay, let's unpack this. Maybe start with the different layers of storage. I sometimes think of it like a pyramid.
That's a great way to put it. Or layers of access, like you said. At the bottom, you've got storage that's vast, but relatively slow.
And as you go up,
It gets smaller, much faster, and significantly more expensive per unit of storage.
right. So our source outlines three main types in this hierarchy.
That's right. At the widest, slowest layer, you have the hard disk.
Ah, the classic hard drive where everything lives long term.
Precisely. Your operating system, programs, files, everything that needs to stick around when the power's off, it's non-volatile.
Meaning the data persists.
Exactly. Capacity is huge. We're talking terabytes now. But speed, it's the slowest layer. Hundreds, maybe low thousands of megabytes per second.
And cost-wise,
Cheapest by far. Cents, maybe a few dollars per gigabyte. It's bulk storage.
okay, that's the archive layer.
Yeah.
What's the next step up towards the CPU?
That would be random access memory. RAM.
Okay, RAM. The computer's active workspace. All right.
Exactly. It's temporary storage for programs and data the CPU is actively working on right now. But unlike the hard disk, RAM is volatile.
Power goes off, data disappears.
Poof, gone. Its capacity is much smaller than a hard disk, usually gigabytes, but it's way faster, tens of gigabytes per second transfer rates.
And the cost reflects that speed, I assume.
It does. More expensive than hard disk space. You're looking at tens, sometimes hundreds of dollars per gigabyte.
Okay, so hard disk for permanent storage, RAM for the active stuff. What's at the very peak of this pyramid? Closest to the processor.
That's cache memory.
The really tiny, super fast layer. Almost sounds like magic.
It kind of feels like it.
Yeah.
Cache is designed to hold a tiny fraction of data and instructions, specifically the stuff the CPU is using most frequently or is predicted to need, like right away.
Its whole job is avoiding trips to RAM.
That's the goal. Keep the CPU fed without waiting for slower main memory. Like RAM, it's volatile. Capacity is tiny megabytes, usually, split across levels like L1, L2, L3.
But the speed is incredible.
Incredible. Often hundreds of gigabytes per second, nearly matching the CPU core speed. And because it's so fast and tightly integrated, it's the most expensive memory, usually priced right in with the CPU.
So it's a fascinating hierarchy. But why not just make all storage super fast, like cache? Or, just use RAM instead of hard drives. Seems simpler.
Well, that hits the core engineering trade-offs. The source explains this well. This whole layered system is a deliberate balancing act between speed, capacity, and cost.
Okay.
Replacing hard disks with RAM, for instance. Two huge problems. First, volatility.
Right, you'd lose everything every time you shut down. Not practical.
Not at all. And second, the cost. Imagine paying RAM prices for terabytes of storage. It would be astronomically expensive.
Okay, point taken. Volatility and cost rule out RAM for bulk storage. What about the other way? Just makes the cache massive if it's so fast.
Wouldn't a huge cache solve everything?
Yeah.
That's the other key trade-off, especially with cache. As you make cache physically bigger to hold more data,
Let me guess. It gets slower.
well, the signals have farther to travel. A larger physical size means the cache circuitry is farther from the CPU core doing the work. Increased distance means higher latency.
So making it bigger starts to counteract the speed benefit.
Exactly. It's a delicate balance. That's why we have multiple levels, L1, L2, L3, trying to find the sweet spot between size and proximity.
That makes sense. My desk analogy kind of holds up then. My desk is the cache, small, everything's instantly reachable. Filing cabinet is RAM, holds more, but takes a step. Offsite storage is the hard disk huge, but a real trip to get anything.
That's a really good way to visualize the access times. And think about the data flow, like figure 410 in the source shows. Data moves from the hard disk into RAM to be worked on.
The CPU doesn't usually touch the hard disk directly for processing.
Right. It works primarily with RAM, and the cache sits right between the CPU and RAM. It's constantly trying to pull in small chunks of data from RAM.
That it thinks the CPU will need next.
Precisely. It's anticipating. By keeping the most likely needed data incredibly close, the cache cuts down on those slow trips to RAM.
Which speeds everything up.
Massively. It boosts the overall efficiency of program execution.
Okay, this is where it gets super relevant for anyone dealing with data or code. How do fundamental structures like, say, arrays and linked lists actually use this memory system? And how does that explain why one might be faster than the other in certain situations?
Great question. It starts with how efficiently they use the available memory space. Remember, RAM isn't infinite, it's limited and shared.
Like packing a suitcase space. Efficiency matters.
Exactly. Let's look at arrays first. Their key feature is storing elements in a contiguous block.
Meaning right next to each other, one after the other.
Yes, in a single, unbroken sequence in memory. This is very space efficient for the data itself because you don't need extra memory between elements to find the next one. You just calculate its position.
But there's a catch, right?
The catch is you usually need to allocate that contiguous block up front. Guess the size. If you allocate too much, you waste space. If you run out,
Expanding is painful.
it can be. Expanding often means finding a new, larger, contiguous block somewhere else in memory and copying everything over. That takes time.
Okay, so arrays are tightly packed but can be rigid. What about linked lists?
Linked lists offer way more flexibility with size. Each element or node is allocated individually. They don't need to be next to each other in memory at all.
That sounds good.
It is flexible, but there's an overhead. Each node needs extra memory just to store a pointer.
A pointer, like an address.
Exactly, an address that tells the computer where the next node in the sequence is located in memory.
Ah, so linked lists are flexible, but each element costs more memory because of that pointer.
Correct. And this relates to something called memory fragmentation. The source mentions this too. As programs run, allocating and deallocating chunks of memory all the time.
Free memory gets broken up.
Yeah, into lots of small, maybe unusable gaps. Reduces how effectively you can use the total memory. It's like having lots of little storage spaces instead of one big one.
Makes sense. So how do arrays and lists play into that?
Arrays, needing that one big block, are less likely to cause this kind of fragmentation within their own data. They grab their space and hold it. Linked lists, though, with nodes scattered all over and frequent allocations, deallocations.
They could make fragmentation worse.
They potentially can, yes, because they sprinkle small allocations throughout memory.
Okay, so summarizing memory space. Arrays tend to be more space efficient for the data itself and cause less fragmentation, but linked lists win on flexibility for dynamic sizing.
That's a good summary. Now let's jump back up to the cache. We said it's tiny but critical for speed.
Right, because RAM is slow compared to the CPU.
Exactly. So when the CPU needs a piece of data, it first checks the cache. If the data isn't there, that's a cache miss.
And that's bad.
That's bad for performance. The CPU has to pause, basically, and wait while the data is fetched from slower main memory, RAM. That wait time is latency.
And if the data's in the cache?
That's a cache hit success. The CPU gets the data almost instantly and keeps humming along.
So the goal is to maximize hits.
Absolutely. The cache hit rate, the percentage of memory accesses served by the cache, is a key performance metric. Higher hit rate equals faster execution.
It almost sounds like modern computers are fast only because of these cache hits, given how slow RAM is relatively.
You're absolutely right. That's a key insight. The cache and all the clever mechanisms around it are the hardware's main strategy to bridge that speed gap between the CPU and RAM.
So how does it try to maximize those hits? What are the mechanisms?
Well, the source details a few crucial ones. First, caches don't work with individual bytes. They load data from RAM in chunks called cache lines.
Like grabbing a whole paragraph instead of just one word.
Sort of, yeah. When the CPU requests data at address X, the cache might pull in a 64-byte or a 128-byte block, the cache line, containing X and its neighbors.
Why do that?
Because of spatial locality. This is a fundamental principle. Programs tend to access memory locations that are near locations they just accessed.
So if I need X, I'll probably need X plus 1 pretty soon.
Very likely. By loading the whole cache line, the hardware is betting on spatial locality. It brings in the neighbors automatically, hoping they'll be needed next.
Clever. It's anticipating based on proximity.
Exactly. And it gets more sophisticated. Processors also use a prefetch mechanism. They don't just react, they actively try to predict future access patterns.
Like if I'm stepping through an array.
Perfect example. If the processor sees you accessing array elements sequentially, it might start preloading the next few elements into the cache before you even ask for them.
Wow, so it's trying to stay ahead of the game.
Definitely. And then there's temporal locality, another key principle. If you access a piece of data now,
You'll probably need it again soon.
high probability. So caches use algorithms to keep recently accessed data hanging around in the cache for a while. This increases the chance of a hit if you need that same data again quickly.
Okay, so we have cache lines, spatial locality, nearby data, prefetching, predicting patterns, and temporal locality, recently used data. These are the cache's tricks.
They are the hardware strategies, yes, to make the cache as effective as possible despite its small size.
Now, finally connect this all back to arrays and linked lists. How do their different structures interact with these cache mechanisms? This feels like the core of the performance difference.
It absolutely is. The physical layout directly helps or hinders these cache strategies. And our source clearly explains why arrays generally get a higher cache hit rate and thus better operational efficiency.
Okay, bring it down for us. Why are arrays usually more cache-friendly?
Right. First, think about occupied space again. But now in the cache, remember, linked list nodes have that pointer overhead.
Takes up extra space.
Right. So for the same limited cache size, you can fit fewer actual data values from a linked list compared to tightly packed array elements. The cache gets filled with less useful payload, more overhead.
Okay, arrays are more data dense within the cache. Makes sense. What else?
Second, cache lines. Remember, data loads in blocks. Array elements are contiguous, right next to each other.
Yeah.
So when the cache loads a line containing array element E, that same cache line is extremely likely to contain elements I plus 1, I plus 2, and so on.
All useful neighbors for sequential access.
Exactly. It perfectly leverages the cache line mechanism. Now, contrast that with linked lists. Nodes are scattered. When a cache line is loaded containing node A,
The rest of that line might be totally unrelated data.
precisely,
Well-
because node B could be anywhere else in memory. So the cache line gets loaded, but maybe only one small part of it, node A, is actually useful for traversing the list right now. Much less efficient use of the cache line.
Got it. More wasted space fetched for linked lists. Next.
Third, the prefetch mechanism. We said processors predict patterns. Accessing an array sequentially is a very predictable pattern.
Easy for the prefetcher to guess the next address.
Trivial. It just adds the element size. But for a linked list, where's the next node? The processor doesn't know until it actually reads the pointer inside the current node.
So it can't effectively prefetch the next node's data.
Much, much harder. It has to wait for the current node's data to arrive, read the pointer, then it knows where to look next. Prefetching largely breaks down.
Like hitting a dead end at every node until you read the signpost?
That's a perfect analogy. And finally, maybe the biggest factor, spatial locality.
The principle that nearby data will be needed soon.
Yes. Arrays embody spatial locality. Their elements are physically stored next to each other. Accessing element I makes it almost certain that element I plus 1 is the physically adjacent data the cache just loaded.
Perfect alignment.
Perfect. Linked lists, by design, break spatial locality. The next logical node in the sequence could be physically located anywhere else in memory. Accessing node A tells you nothing about whether node B is nearby.
So arrays naturally play well with all the caches, strategies, density, cache lines, prefetching, spatial locality.
Exactly. Their contiguous structure is just inherently cache-friendly. This is why, as the source points out, array-based structures often show much better performance, especially when you're iterating through them or accessing elements sequentially.
Which happens a lot in algorithms.
It's a huge amount, yes.
But, okay, despite all these cache advantages for arrays, linked lists obviously still exist and are used heavily. So arrays aren't always the best choice, are they?
Absolutely not. The source is clear on this too. The choice always comes down to the specific needs of your application. Cache efficiency is important, but it's not the only factor.
What kind of needs would make you choose a linked list despite the potential cache hit rate penalty?
Flexibility is the big one. Remember the array's downsides.
Yeah.
Fixed size, pre-allocation, the potential cost of resizing.
Right.
The source uses implementing a stack as an example. In many algorithm problems, you know roughly how big the stack might get. An array-based stack is often preferred then.
Because it's fast and cache friendly.
Yes, and the cost of pre-allocating is acceptable. But imagine a different scenario. You need a stack for, say, a system dealing with massive, unpredictable amounts of data. The stack might grow huge, then shrink, then grow again. You have no idea upfront how big it needs to be.
Using an array there sounds risky. You might waste tons of memory allocating too much or constantly hit that expensive resizing operation.
Exactly. In that situation, a linked list-based stack might be much better. You allocate nodes only when needed. It handles massive dynamic sizes gracefully without that array resizing penalty.
Even though traversing it might be slower due to cache misses.
Yes, because the flexibility and avoidance of huge pre-allocation or resizing costs outweigh the cache inefficiency for that specific use case. The memory might be scattered, but you gain crucial adaptability.
Okay, that really clarifies the trade-off. It's not just about raw speed. It's about matching the structure's strengths and weaknesses, including memory and cache behavior, to the problem you're solving.
That's the key takeaway. Understand the problem, understand the structures, understand the memory hierarchy they live in.
Wow. Okay, what a journey. We went from the basic storage pyramid hard disk, RAM, cache, through how arrays and lists use memory space and deal with fragmentation, and then really deep into cache mechanisms like locality and prefetching. Seeing why arrays often benefit more, it gives such a clear picture of the performance implications.
It really connects the low-level hardware reality to the high-level data structures we use every day.
Understanding this makes you think differently about performance.
It absolutely should. And maybe here's a final thought for you to ponder, extending this idea. Knowing how much performance hinges on efficiently accessing data on locality.
Hmm.
How might these principles apply outside of coding?
Like in everyday life.
Yeah. Think about how you organize your physical workspace, your digital files, your notes, even the tools in your kitchen. Are you implicitly using spatial locality, keeping related things together? Are you using temporal locality, keeping frequently used items easily accessible, like your personal cache?
Huh. Optimizing my personal cache hit rate.
Exactly. How does the way you organize information impact how quickly and efficiently you can access and use it? It's kind of the same fundamental problem, just at a different scale, something to think about.